Ultrasonic flow measurement is another type of flow measurement methods. In this slide, we have some basic information about the ultrasound. Ultrasonic waves are sound waves, mechanic sound waves about human hearing, larger than 20 kilohertz. Typical frequencies are between 20 kilohertz to 20 megahertz. Sound waves are longitudinal pressure waves caused by vibration in a medium. Several types of ultrasonic sensors are available. The most common are dynamic or piezoelectric sensors. A typical dynamic sensor is a thin, low-mass diaphragm stretched over passive electromagnet. Such diaphragms operates at frequencies up to 100 kilohertz. And we have two types of ultrasonic flow sensors. Many ultrasonic flow sensors consist of pairs of transducers. Each transducer can operate as either a source or a detector of sound waves. As you can see in this type of ultrasonic flow sensors, we have two transducers, transducer 1 and 2. Each transducer can operate, as I told you before, as either a source or detector of sound waves. As you can see in this slide, the simplified structure of a dynamic ultrasonic transducer. And as I told you before, each ultrasonic transducer can operate as also a generator and also a detector. As a generator of ultrasonic waves, the driver current creates a magnetic field which pushes against the permanent magnet. And as a detector, the motion of the element induces a current in the drive coil. As I told you before, another type of ultrasonic transducer is the piezoelectric transducer. The piezo transmits when an applied potential distorts crystal. We have a crystal with a lattice structure here, and we have a electric field, a fixed electric field inside this piezoelectric material, such as quartz or PVDF, and also the piezoelectric transducer receives some waves when pressure wave distorts crystal. As you can see, we have a structure here with an internal electric field. When we push this structure, the inside electric field, the positive pole will close to the upper side and the negative pole will close to the bottom side, and therefore we have a increased voltage in this structure. And if we stretch this material, the positive and negative poles of the field move away from the upper and lower surfaces of the crystal. And also when we apply a voltage on this material, for example, if we put a positive and negative polarity on this structure, on this lattice structure in the crystal, like poles repel each other and unlike poles attract each other. Therefore, when we put a positive pole at the top and the negative pole at the bottom of this crystal, unlike poles repel each other, and this leads to push the crystal. And if we put a reverse polar structure, reverse polar poles, negative pole on the top and the positive pole for the bottom of this crystal, because the unlike poles attract each other, the crystal will be stretched. And this is the basic rules for piezoelectric, also receiving and transmitting procedure for ultrasonic waves. Why using ultrasonic types? The answer is wide range of applications such as blood, pure water, water, sewage, processed liquid, oils, and other light homogeneous liquids. Clamp-on types measure flow through the pipe without any wetted parts, ensuring that corrosion and other effects for the fluid will not deteriorate the sensor. Clamp-on types simplify and speed up meter installation and minimize maintenance. Ultrasonic flow meters may be portable, and measurement accuracy can be in the range of 1% of flow rate, and the speed of response can be as fast as 1 second. Okay, two types of ultrasonic flow meters are available. The first one is transit time, and the second one is the Doppler ultrasonic flow meters. Transit time is based on calculating the flow rate based on the transit time between a pair of transducer, and this type of ultrasonic flow meters make use of the difference in the time for a sonic pulse to travel a fixed distance between two transducers. Each transducer will act as also transmitter and receiver, first against the flow and then in the direction of the flow. Doppler flow meters use the Doppler frequency shift, and you know this shift caused by sound reflected or scattered from suspensions in the flow path. We need some particles, scatterers, inside the fluid to find the Doppler shift, and after that to find the flow rate. Therefore, transit time do not need any suspension or scatterer inside the fluid, and Doppler method requires something like that to measure the flow rate inside the traveling fluid. Let me explain the basic formulation for transit time flow meter in this slide. As you can see, we have a schematic for conduit here with two sensors, sensor 1 and sensor 2, or transducer 1 and transducer 2. The length between these two transducers, is LW. C is the velocity of the sound, the speed of sound at the operating conditions. Phi is the angle between the axis of the conduit and the acoustic path. This is the axis of the conduit, and this is the axis of the sound, acoustic path, and the velocity of the fluid is VA, axial low velocity average along the distance. And as you can see, we have two time of flight in this slide. Let me start from the first one. Assume that we send a sound from sensor 1 to sensor 2. Therefore, we have a sound speed here, C, and also we have a speed VA here. This is a low velocity, but I show it with this long vector to better display. Because of the path between the sensor 1 and the sensor 2, the projection of the VA cosine phi will affect on the medium speed and will increase the total speed of sound in the direction of sensor 1 to sensor 2. Therefore, the total speed from sensor 1 to sensor 2 is C plus VA cosine phi. And to travel from sensor 1 and sensor 2, LW, we need a time t12 multiplied by the speed of sound in this path, and as you can see, you can find this time by dividing LW by C plus VA cosine phi. In the reverse path, let me write these notes. At the reverse path, when we send sound from sensor 2 to sensor 1, we have a speed of c at this direction because of the speed of sound. But the velocity, the direction of the fluid is as the same as the first condition. And as you can see, the projection of this velocity is at the reverse direction of the sound speed. Therefore, total speed from sensor 1 to sensor 2 is c minus VA cosine phi. And to travel from sensor 2 to sensor 1, LW equals this total speed multiplied by T21. And as you can see, we can find this fraction, LW divided by C minus VA cosine phi. And because of the smaller denominator of second fraction, because the small denominator of this fraction in compared to the first one, T2 1 is larger than T1 2. It means that the sound from sensor 1 to sensor 2 will be received sooner than when we send sound from sensor 2 to sensor 1. Okay, one of your homeworks, we have another homework here, to find the VA by using these two equations. You can find VA based on these parameters and these equations. But there is a mistake, writing mistake in the book. This is 1, 2, and this is 2, 1. Because you know when T2 is larger than T1, 2, therefore this fraction is smaller than this. And because of we don't have any negative velocity at this direction, this term should be positive. And therefore the first one should be larger than the second one. Therefore, the larger fraction should be at the first location, and the smaller should be replaced here. Okay. The correct equation is this, and you should solve this equation. You should find the VA based on the all parameters here. As you can see, we can use the simple nowadays we can simply make such a sensor. We need a piece of conduit, two location for sensors, two fixed sensors with a fixed known length, distance between these two sensors, and you can connect this sensor to any path of a fluid to measure the velocity of the fluid inside that sensor. But as you know, and as I mentioned before, Doppler effect is a shift in frequency from a moving source of waves. We have a source of waves here. If all parts in the environment is fixed, the reflected sound will be reflected with the frequency of the source. But if these parts, if these objects in the environment start to move, the speed of this movement will affect the reflected frequency, and it leads to a shift of frequency, and we call this shift Doppler effect or Doppler shift. And we can use this Doppler effect to measure the velocity of a fluid. As you can see, we have a transmitter and a receiver sensor inside our sensor box. We have an incident sound. This sound will hit to the particles of the blood. We call these particles, these comparable particles, scatterer. These scatterer will reflect the sound to the receiver. And because of their movement, the reflected sound will reflected by a new frequency. And the shifted frequency is proportional to the velocity of the fluid. Therefore, we can calculate the flow rate. As you can see in this slide, we have a sender here and a receiver here. We have a moving object. As I told you before, the blood cells in the fluid scatter the Doppler signal diffusively, and As you can see, the shifted frequency can be calculated by this simple equation. Fd equals 2 multiplied by Fc, the center frequency of the sender, and V, the velocity of fluid, C, the velocity of sound, speed of sound. In recent years, ultrasound contrast agents have been used in order to increase the echoes. And also, the ultrasound beam is focused by a suitable transducer geometry and lenses to focus correctly on the moving objects. On the other side, we have some um, problem problems with this focusing issue. We should stay focused on the moving objects, on the on the fluid path to maintain the accuracy of our measurements. And as you can see, some examples of numbers to find the FD. Remember that the FD, the shifted frequency, is proportional to the center frequency, also to the velocity of the fluid. These are important. These are important issues because we will use these relations to tune, to propose some fabrications, some devices, some designs in Doppler measurements. In Doppler measuring system, we have two types of waves, continuous waves and pulse waves. Continuous wave systems use continuous transmission and reception of ultrasound. Doppler signal are obtained from all vessels in the path of the ultrasound beam, high velocity, and pulse wave transducer both sends and receive the signal. It tends in short bursts and receives in the time when it is not sending. I skipped the explanation of this slide, but you should remember that some parameters will affect the power of the ultrasound signals inside the tissue. Therefore, we should consider these parameters. We have some limitation of Doppler flow meters. The first one is related to the liquid. Liquids to be metered must have an excess of approximately 2% suspended solids by volume. And also liquid linear velocities must be exceed 0.15 meter over second. Piping material must be of a homogeneous composition, and also pipe wall thickness cannot be greater than 1.91 centimeters. Similar to ultrasound, we have such a shift in frequency in laser. Laser Doppler flowmetry is another type of flowmetry based on Doppler, but the basic wave in these flow meters is light, laser light. The principle of measurement is the same as with the ultrasound Doppler. The laser parameter may have be, for example, the following properties, as you can see here. 5 milliwatt helium neon laser and a specific band width or wavelength here, 632.8 nanometers. And the moving red blood cells cause Doppler frequency from 30 to 12,000 hertz. And the method is used for capillary microvascular blood flow measurements. As you can see, we have a helium neon laser light here. It generates a laser and we send it to the tissue and we target the capillary loops. As you can see, the final target is the capillary loop, and because of some cells like erythrocytes here, the reflected light has two parts. The first one is as the source frequency, source bandwidth, and the second is shifted frequency, shifted light, and therefore the phototube will receive two frequencies. And using these lights, we can find the flow of the blood inside the capillary loop.